Okay. Uh, Hello, everyone. Welcome to this month's Lunch and Learn entitled Introduction to the Splunk Machine Learning Toolkit. We appreciate your time today and we believe that you'll come away with some interesting information. Today's session will be delivered to you by Jim Baxter, who is a Splunk architect and has a keen interest in machine learning. Jim has provided professional services to many customers and has contributed to the performance and capacity analytics element in the Atlas framework here at Kinney Group. And now, with that, I will turn it over to Jim.
Okay, good afternoon, good evening, depending on where you are. Appreciate your time here. Thought we would go through the Splunk Machine Learning Toolkit. I'll come up with an agenda here. I'm going to make a couple of assumptions, want to level the playing field, if you will. I'm going to assume that, like me, when you first maybe opened up the Splunk Machine Learning Toolkit, the MLTK, and took a look around, you didn't find it as intuitive or easy to work with as you might have hoped. And you poked around a little bit and thought, okay, and kind of closed it down and went on with your day. You've probably heard, machine learning and AI, it's the thing these days. And there's a lot of terms that get floated around. And unless you spend a lot of time in this arena or have been doing it a while, some of these terms are, again, a little less than intuitive, a little intimidating, what have you. So the idea today is to do, as per the agenda, a whirlwind review of some of the machine learning categories, the algorithms you'll hear used, and some use cases. And because machine learning, is a subset of artificial intelligence, because a lot of machine learning is based on probability and statistics, do a quick review of statistics, just the top level stuff, in case it's been a while since you've had a statistics class, or maybe you haven't had one at all. And then I want to work through kind of developing what I use as a mental model of how to work with the machine learning toolkit. Makes it a little more intuitive to work with, some data preparation steps, how you can use it with your data, and then a kind of a demo and deep dive into several of the showcases and an experiment and something you could actually use in your own environment. So let's get started. All right, categories. Machine learning falls under several of these. First is supervised. Supervised just simply means that you're using data that has been labeled, whatever that label means, whether it's, good grief, whether the, sorry, I lost my train of thought there for a second. Whether it's spam or it's not, whether it is a threat, a security threat or not, or what have you, a failed hard drive, those kinds of things. You feed the model that labeled data to train it, and then you apply that model that's learned on that data against data that it hasn't seen before. Usually you take if you have a data set you're going to train with, you will divide that up into two pieces. One is a training set, which is about 70 to 80% of the total data set. And then you'll do testing on the remainder after you've trained the model to see how it did on data that it hasn't seen before. If it doesn't work out so well, maybe you tweak a few parameters, go through the cycle again. Use cases for supervised models is classification. That's, whether it's spam or not spam, fields in an email, from fields in an email, like who it's from in the subject line. Or maybe it's regression. It's, what's the house price based on the square footage in a given neighborhood? Those kinds of things. Some of the key algorithms, linear regression, logistic regression, we'll talk about those in a minute. Support vector machines and random forest. Another major type is unsupervised. That's where the algorithm divides the data up based on its own characteristics. You think like groups of consumers that are based on purchasing behavior, demographics or preferences and what have you. Whatever patterns or structures are in the data. And the use cases is clustering, grouping similar data points together. Again, this is that like customer segmentation, or identifying anomalies. If there's a big cluster, what's normal, and you've got something outside of the cluster, maybe that's an anomaly. Those kinds of things. Algorithms for this is k-means clustering. We'll see this later on. Principal component analysis, independent component analysis, and so on. Reinforcement learning. This is where you have a model that is learning by trial and error. For every action that the model takes, there is a reaction, there is a new state, if you will, but there's also a reward value. And the model tries to resolve to the highest reward value. And it kind of learns from, an iterative process. Some use cases for that's like robots learning how to navigate a maze or play a game, resource allocations, or maybe even learning how to escape into the internet and take over mankind. That's the same kind of thing there. And there's a couple of other additional categories. Semi-supervised learning. It's not quite as intuitive. It might have to do like if you have some labeled data, but you don't really have a lot of it. And then you take some unlabeled data and you kind of run that against the model after you trained it on the labeled data. And it comes up with a handful of outputs where there's a high confidence level, high probability that it's made the right decision there. You might take those outputs and feed them back in and add them to the original data set, and then retrain the model on the newer, larger data set to improve its accuracy. And so on. So anyway, and then there's deep learning. Now this is the AI side of things. This is where you have your neural networks with their hidden layers, various inputs and 1 or 2 or 3 outputs and what have you. And then those are divided into, several other kinds of groupings like convolutional neural networks, used a lot for vision processing. Recurrent neural networks is like predicting the next word. That's like, where you're typing on your cell phone and it predicts the next word for you and what have you, that kind of thing. Bag of words, you may have heard that term. Generative adversarial networks, where 2 neural networks are competing against each other to kind of help fine tune, like sharpen the saw concept. And then finally, transformers. You've heard about ChatGPT. That's based on transformers, which, it works on understanding relationships between words and so on. All right, so let's get into algorithms. Regression is one that you'll see in here most of the time. It's used to model the relationship between continuous is the term. That means changing or related variables or values. It calculates an output based on an input value. It's like you see over here in the graph on the right-hand side. That blue line is trying to fit to be closest to all of the data points in the data set. It ends up becoming a slope. You might remember that from algebra, I think it is. And this line is the best guess for predicting, like in this case, price based on housing size or what have you. Works best for linear relationships where there's a straight line, but there is also a polynomial regression that'll work with curved data sets. There's logistic regression. I think of that as a true or false, this or that, kind of binary output based on various input parameters. It can handle both continuous and categorical features. And it assumes that there's a linear relationship between the features and the outcome, which may or may not be true. And this one is not ideal for what's called multi-class classification or more than 2 outputs. This is really a yes or no, true or false kind of algorithm. Support vector machines. These are a fairly complex little beastie. They are used for like handwritten digit recognition in postal automation. They can work with multiple dimensions, if you will. But what they really try to do, if you look at the image on the right-hand side, you see the little pluses and the minuses. They try to identify what they call a hyperplane between these clusters of data sets. And the support vector is a term that's applied to the points that are closest to this separating hyperplane. Again, it's kind of a complex little beastie. Won't spend too much time on that here. Random forest. Random forest is probably one of the cooler algorithms in my mind. It takes a data set divides it up into groups, and applies it to decision trees, if you will. And I like to think of those as kind of like an if then else. Don't know if you remember back in the day, but there was a back in the 80s, if you will, there was a thing called expert systems, and expert systems were really just that. They were if then and else kind of decision trees. And that's what this is about. It divides the data set up into multiple decision trees, and allows each of those to make a decision based on what it sees in the data set. Based on what it sees in the data set. And then the output of each decision tree is kind of grouped together, and there's a final outcome, based on majority rule, if you will. I have found that the random forest is actually a very accurate algorithm. In most cases, it outperforms some of the other even more complex algorithms. Very cool stuff. Then there's k-means. K-means is a way of clustering data sets based on what their average values lead you to, if you will. You can see here in this little illustration on the right, one of the things you might see k-means applied to is there's a popular data set for identifying different species of the iris plant. That data set is often used in machine learning training courses, if you will. And that's how this works. Basically, you do specify how many groups that you want to divide the data set into, and you have to get that right if you want an optimal outcome. But it divides it into what is called centroids. It says it's the imaginary or real location that represents the center of each cluster. All right, principal component analysis. It's another one of those newfangled terms. Basically what this has to do with, and again, this is a very complex, if you dig into the details, a very complex algorithm can be, but at the high level, what it's trying to do is, if you imagine a data set that has a lot of different features, as they call them, or fields, if it's a data, like data you might put into Splunk. And a lot of those fields, or a number of those fields, if you will, have very similar characteristics. They kind of reflect each other. In my brain, Windows event logs, for example, come to mind. There'll be numerous fields in there where they all kind of really say the same thing. Some of our security technologies do the same thing. The logs have a number of fields that really are all about the same basic metrics. PCA helps to reduce that data set down. It'll take, say, 3 different fields that really have a high covariance, as they call it, where the data basically says the same thing. And it'll create one new field and eliminate the other 3, so that your machine learning model doesn't have to work with as many data points, or as many features, and reduces the complexity and the processing costs and what have you. So really that's what PCA is about. But again, it can apply to a lot of dimensions. It can get very complex if you want to get into the weeds with it. Oh, by the way, the data point at the bottom of this slide, the data will typically need to be normalized, which we'll touch on here in the next slide. That means taking extreme values or various sizes or ranges of values and kind of reducing those into something a little more manageable. Here we are. Let's talk about normalization. There's several types. Min-max scaling will take a range of numbers and basically kind of linearly convert those into a range between 0 and 1. It's simple. It's efficient. It is sensitive to outliers. If you can imagine that you have a range of numbers that are, say, within 50, and then you have one hanging out there that's 250 away, it's obviously going to affect the way the scaling works and reduce your accuracy, if you will, the sensitivity, if you will. There's standard normalization, also known as the z-score, where it tries to transform the range of numbers into a standard distribution, having to do with a mean of 0 and a standard deviation of 1. And then finally, there's L1 and L2 regularization. It's kind of a complex term. Basically, it's trying to reduce the complexity of a data set by penalizing either really small numbers or kind of the more complex or extreme numbers, using some of these crazy formulas you see over here on the right-hand side. By the way, I'll make a comment here. The algorithms that you use for machine learning in the Machine Learning Toolkit user guide, for example, it will identify those algorithms that work much better with normalization. So you don't have to try to guess this one on your own. All right, so once you have your algorithm has done its magic against your data set and has created some outputs, you need a way to identify how accurate that output is. And the method you use for that varies depending on whether you're doing, in this case, for this slide, classification. For example, if you are looking at a bunch of tissue samples and you're trying to figure out whether they have a tumor in them or if they're cancerous and what have you, it's really important that this is as accurate as possible. So the primary way this is done, for example, is you have what is known as precision and recall. And this is one of these things you got to kind of work with this stuff a while before that starts to sink in and you get comfortable with it. I'm not always sure that I'm comfortable with it all the time. I don't do this kind of thing all the time. But basically, it has to do with how many accurate predictions were made based on the total number of predictions that could have been made or were made, true positives, true negatives versus the false positives and negatives, and so on. So that's precision and recall. F1 score is kind of a derived combination of those two. And then finally, accuracy is just the number of correct predictions out of the total number of examples or predictions made. Regression scoring, this is more like the line that we were seeing previously with linear regression, has to do with how well the line fits the data set. How close do we get to as many points as possible? And this is a pretty simple calculation, really. It's just the measurement of the data point, each data point, and how far it is away from that mean line, the average line, if you will, that goes through the data set. And this is called the mean squared error. Basically, they square it, they measure it, and they square it, which gets rid of the fact that one may be above the line, one may be below the line. If you square it, it basically does an absolute value, but it's a large value. So if you take the square root of that, that's the root mean squared error, RMSE. And then R squared is a proportion of the variance explained by the model. And that is a number between 0 and 1 or 0 and 100%. We'll see those when we get into actually using the machine learning toolkit. All right, so that's enough about all of those things. Let's talk about statistics for just 5 minutes. You may have heard people say that machine learning is just applied statistics, or that statistics is just applied probability. These are rooted in truth. I may have said some of those things myself. There's a lot of statistics in machine learning. Machine learning heavily utilizes statistics, and statistics is based upon probability theory. You've heard of Bayes' theorem, for example. Probability enables us to reason about uncertainty, and statistics quantifies and explains that uncertainty. Machine learning makes predictions from data, and it might use probability or statistics, and it might not. So let's discuss just the statistics you need if you're going to dabble in anomaly detection, which is one of my favorite, if you will, areas of machine learning. Actually, it's the one that I've spent most of my time in. What time I have spent. By the way, I'm going to make the comment here. I label myself as a machine learning practitioner. I didn't say engineer. I didn't say expert. I've been dabbling with machine learning for well over a decade, taken a number of courses, read quite a few books, done a lot of exercises, and created some machine learning solutions for some clients. But I do not consider myself an expert. It's a very wide and deep field, depending on where you want to go in it. Most of my time has been spent dabbling in the anomaly detection side of it. I think that's the most useful part for what I do for a living. So there's that disclaimer. All right, let's talk about mean, median, and mode. You will have heard these. Mean, of course, is the average, the number of samples all summed up and divided by the number of samples. And you can see from this illustration here that if you have a normal distribution of data, which is common in the real world samples, the mode, median, and mean will be very close to each other. But your data can have a left skew or a right skew, in which case those numbers will vary. Variance. We talked about this when we were talking about root mean squared and root mean squared error. That was the measurement of how far each number varies from the average. Again, here's the same line with data points above and below it. We treat all deviations from the mean as the same by squaring them. And that variance, of course, being a squared number, you see the formula here on the right. By the way, these formulas sometimes look kind of mean, but this one is not too hard really to understand. If you look at the top there in the parentheses, you take xi, which is your data point, and you subtract the mean from it, and you square that number. You take the sum of all of that, and then you divide it by the number of samples, just like you would for an average, and that gives you your variance. Again, that's a fairly large number, and it doesn't really fit, if you will, for the size of the data points that you're working with. But if you take the square root of that number, you end up with the common term, standard deviation, which is in the same range as the data set that you're working with. So standard deviation is the number that you'll work with the most. You can see from the graph in the bottom that if the standard deviation is like 5, the data is fairly grouped together. If there's a lot of variance in the samples, you'll see that that spreads out significantly, like the right-hand side of that graph. All very straightforward stuff. And finally, let's look at this thing on the right-hand side. This is worth absorbing, if you will. This is a standard model, standard normal distribution. And you can see that the little u, which means the mean, is in the middle. And it kind of curves off to either side. What's interesting about this is that the green segment, if you will, is one standard deviation away from the mean, and that captures or represents, if you will, about 68% of the data samples in your collection. 2 standard deviations, you've gotten about 95% of your samples. 3 standard deviations, you've got 99.7% of your samples. So you can see how that kind of captures that data. The standard deviations are also known as z-scores. You'll hear that term thrown around a lot. And because of that 3 standard deviations representing all but about 0.3% of your samples, that's a very useful model, or metric, I should say, to use with anomaly detection. Keep that one in mind, even though I have ended up using about 5. Last minute, percentiles and interquartile range. Percentile is a value on a scale of 0 to 100 that indicates the percentage of a distribution that is equal to or below it. In other words, if a 95th percentile is a number that represents the fact that 95% of all your sample data is at that number, that value, or below it. It's kind of like a bucket of 95% of your samples. I want to make the comment that these are, I love 95th percentiles. I've used them for a couple of decades now. I've done a lot in previous lives, done a lot of performance modeling, capacity planning, network bandwidth projections and application performance projections and what have you. And for capturing those kinds of metrics like bandwidth and latency and what have you, I've used 95th percentiles because they're good for capturing the bulk of the data, but leaving that top 5% out gets rid of a lot of those outlier values that can really hose you up. I'll come back to this in the next slide, but just keep in mind the 95th percentile is a good metric for that kind of stuff, and so on. Finally, there's the interquartile range. That is the range for the middle 50% of your sample data. Typically, if you look over here at the box plot on the right-hand side, that lower quartile will typically be a 25th percentile. The upper will be a 75th percentile. So that 50% of stuff in the middle is the interquartile range. And these are used for anomaly detection and other kinds of things in machine learning. So you'll see it from time to time. Again, in this box plot, you can see what's called the whiskers, which are the numbers that go above and below those interquartile ranges. To the upper and lower extreme won't necessarily be, the lower won't necessarily be a 0, as you can see here. And then you might have some outliers, little dots above and below those other percentiles. Steve mentioned the performance capacity analytics element that just got added to our Atlas product. I want to say that I used the 95th percentile for a lot of that stuff, like CPU utilization and so on. Again, I want to make this point. If you look at the graph on the right-hand side, this is a graph of CPU utilization based on 10-second samples. This comes from Splunk, and we'll use this later on in the MLTK demo. You can see that purple line at the bottom. That's the average CPU utilization. 10-second samples with 5-minute summaries, if you will. We're taking the, say, the stats. In this case, we're using time chart, which does the same thing. And it's taking all of those 10-second samples and gathering, grouping them together into 5-minute sample periods. So the average is the purple line at the bottom. The green is the max. That is, you could have had, one 10-second sample where the CPU utilization was extremely high. And you'll see that represented in this green line. But that doesn't represent what's gone on most of the time with your cores. The 95th percentile, that magenta line you see there, is a very nice representation of what typically goes on without being unduly affected by outliers, or short-term peaks, and without, the average. The average is just useless for this kind of work. I'll just say that. All right, wrapped up with all that coverage. A couple of common use cases. I've talked about anomaly detection quite a bit. It's good for unusual system behaviors, network traffic, server logs, CPU utilization, application transition, response times, you just name it. Anomaly detection lets us identify when something is out of kilter. Predictive analytics, you'll see a lot of this in the IT service intelligence premium application. It tries to look at what's typical for across a spectrum of data metrics, if you will, and start identifying when something is starting to go wrong. And ideally, I'd warn you and let you know, what's happening before it completely fails, and then you can either fix it or at least schedule some downtime or what have you to address it before it causes a downtime. And then finally, you've heard of, enterprise security uses a lot of machine learning for correlation searches, looking across multiple metrics to say what is normal and what is not, to detect security threats and so on and so forth in real time. All right, so now we're ready actually to get to why we all came here today. Let's play with the machine learning toolkit. Before we can do that, we have to install it. You may or may not be aware that it runs all those algorithms and utilities that it uses are based on the Python for Scientific Computing add-on, which needs to be installed preferably before. I think you can install it after, but it works better if you do it before. And there's different versions of that for your Mac, your Linux, or your Windows environments. I have run across situations, and I don't remember the details of what it was, but I have sometimes had to manually unpack that sci-fi toolkit package, if you will. It's fairly large, and the Splunk UI web installer, it just didn't work right. So you can manually unpack it into the Etsy apps directory. Then install the machine learning toolkit on top of that. You're ready to go. I'm going to highly, highly, highly recommend that you spend some time in the Machine Learning Toolkit user guide. Yes, it's a thick document. It's got lots of stuff, kind of intimidating. But if you break it into sections, it's not so bad. And as you'll see me try to do during this demo, you can also refer to it while you're working with the MLTK, and it becomes a little more pointedly useful, if you will, in that. But I do recommend you peruse the algorithms section. There's a lot of algorithms that are standard in the MLTK. The scoring, we've talked about some of the scoring methods. There's a number of other scoring things and some details about that. And then finally, the showcase sections, which we'll dabble in that today, but it goes through all the examples of the showcase and experiments, and we'll walk you through that stuff. So I'm going to take this point too to make this comment. I don't know about you if you've done any programming or not, but I find trying to learn something like programming in a new language, arduous is probably the best word, unless I'm trying to write code to do something that I'm interested in. If I have a purpose for writing the code. then I don't mind. I enjoy the journey. It's fun. I learn. It sticks, etc. I think the same thing is true of the machine learning toolkit. There is a quick reference guide. The link's here at the bottom of this slide. And you can use that to kind of help you get started. But really find something that you want to do, anomaly detection. There are showcases. There are also deep dives in the MLTK user guide. There's a section in there called the deep dives that will take you through some really interesting and useful applications for different kinds of machine learning applications and algorithms. And I think you will find that that's the best way to approach this, besides just getting in and getting some basic familiarity, which I'm hoping to help you with today. I also want to introduce my way of thinking about the MLTK. Again, when I first started looking at it, it wasn't real intuitive, and it was kind of deep, and I don't know. I didn't spend a whole lot of time in it the first time or two. But after a while, I started realizing that I needed a simple mental model, way of approaching it. And here's what I'm going to suggest that works for me. The MLTK is really just a wrapper and a user interface around these common machine learning algorithms that come with the Python scientific kit. It provides drop downs to select, the fields to predict on, the machine learning algorithm you're going to use, some of the parameters or parameters that you have to use with those algorithms. It provides that user interface. It's kind of friendly. And as you'll see in a little bit, it actually goes through and will run the predictions, if you will, and then do the scoring at the end. It does all that for you, so you don't have to kind of figure that stuff out. Helps you, it's like training wheels, kind of helps you get started. And the other point I want to make is, in the end, it's really just the search processing language that you're going to use that comes out of this MLTK user interface. You can click a button at any time and see the SPL that it's using to do what it's doing. That's what you'll end up using in your production environment, along with the fit and apply commands. The fit is where you train the model. Apply is where you take a model that's already been trained and you apply it to a new set of data. And that's really all it boils down to. It's just training wheels for machine learning algorithms. Last point, I kind of already touched on this. You don't have to eat the entire machine learning elephant. It's a big pig. Find something that pushes your button and sit down and learn the algorithms, the parameters it uses, do some experimentation, and just get in there and get your hands dirty. And before long, you'll feel comfortable with it. All right, I'm going to skip these next couple slides, so they're really just kind of outliers, if you will, for what we're going to do as a demo, because I found earlier in the day that sliding between my presentation deck and the demo environment was not as easy as I would hope for it to be. So I'm going to do the last couple of slides now, and then we'll go to the demo. Finally, data cleaning. You may have heard, if you've dabbled in machine learning for a while, that 80% of the work that you'll do is cleaning the data. Well, hopefully, if you're working with Splunk data, it's not that bad. But you will have data sets sometimes that have missing values. And a lot of these algorithms don't deal with missing values very well. You may want to get rid of outlying values ahead of time. If you know what they are and how to find them and get rid of them, you might want to do that. You want to make sure your formatting of the data fields is consistent. Get rid of duplications and so on. Feature engineering. That's that part where we talked about, reducing the number of fields that you work with. And you might be able to do that just by selecting specific fields to use as inputs to your algorithm. But you might want to do a little PCA or what have you. And the MLTK gives you the opportunity to do that. Scaling, you'll find a number of these algorithms you see at the bottom of this slide will say that they need to be, have the inputs normalized, if you will. The standard scaler is commonly used for that. It does that. It does that scaling for you, and there's the syntax for it. Missing values. There's a fill null command. You might have used that in Splunk for other things. You can specify a value to fill it with, and then finally, there's an imputer algorithm, which is really cool because it will look at if it comes across you specify a field. If it comes across an entry where there's nothing there, and whether it's either you can replace it with not a number or an integer, but it can replace it with either the mean or average value from all the other values in that column, the median, or the most frequent, the mode, if you will. Very useful utility for that kind of stuff. Finally, this is kind of really at the end, but I'm going to go ahead and cover this now. References, statistics. There's a book called Introduction to Statistics by a guy named Jim Frost, and he also has a website, Statistics by Jim. This is really nice. He does a really good job of explaining statistics in a way that is easy to understand and kind of fun to learn. Second recommendation there, Statistics in a Nutshell. That's kind of the Bible. It's an O'Reilly book, been around a long time. Machine learning. Lots of good machine learning books out there. One of my favorites is the hands-on machine learning with scikit-learn, Keras, and TensorFlow. It's in its second edition. You'll see a lot of other folks recommending that book in the machine learning arena. And then there's a machine learning mastery. This is by a fellow in Australia named Jason Brownlee. He has a number of courses, and they're not very expensive, like $37. And you get a PDF and some additional, worksheets or what have you to go with it. One of the ones I really liked that I took was Mastering Machine Learning Algorithms from Scratch, which he took you through how to do a lot of these algorithms, a lot of them too, in just a spreadsheet, so you can see what goes on under the covers of some of this stuff. It's all just statistics. And then finally, again, the Machine Learning Toolkit user guide. I'll try to show you how I like to use it when we get into the demo thing, which I'm going to try to do now. Let's see, got rid of that. And I'm going to share. Window. All right. I'm hoping that you're seeing my Splunk web UI. Steve, can you confirm that?
Yep, you're good.
All right, good. Thank you. Okay. Assuming you've installed the Machine Learning Toolkit, you'll have an icon down here, look kind of like that. So let's click that. And you come up with the showcase. And the showcase is just, again, this is where you get some example use cases. And we're going to go through a couple of these because it's a lot easier to see what this is good for. We'll click Detect Outliers. And let's look at detecting outliers in server response time. So this thing is going to come up with a search SPL. It's going to load some data from a lookup file that comes with the Machine Learning Toolkit. By the way, there is a lot of good lookups, a lot of good data sets in the lookups folder of the Splunk Machine Learning Toolkit app folder, if you will, and NC apps. Might want to peruse some of that. Looks like it's pulling out a timestamp, and it's doing a chart here across 10-minute samples of the maximum response time. And you can see that we've got this nice little anomaly detection graph. This is based on the median absolute deviation, which is kind of like the deviation from, again, the median, which is the middle value. We can try this with a standard deviation and go like with 3. And let's see what happens when we click that. Okay, I'm not very happy with that. I mentioned 5 earlier. I often find myself using 5 standard deviations just to get rid of spurious things. So that kind of worked okay. But check this out. You remember me talking about the SPL? This is what's going on. This is not even using a machine learning algorithm per se. This is just using statistical stuff. We're doing stream stats to calculate an average and a standard deviation across every 200 data point samples. We're creating a lower boundary by taking the average minus the standard deviation times 5, an upper bound, standard deviation times 5. And we're identifying, this is identifying outliers if our response time is above or below those boundaries. But as I'll show you here, you can also open this and search. There's the data. There's a column chart, but if you have the machine learning toolkit installed, you can go down here and search and find that same visualization. Well, that's not working so good, is it? That's because the outlier chart is looking for this data to be presented to it in a certain format that isn't there when we clicked the open and search thing. So we're going to create a table and we're going to feed it to it in this particular order. And this order is important. We're going to give it the timestamp. We're going to give it the value that we're measuring, response time. And we're going to give it the lower bound. And we're going to give it the upper bound. And we'll hit return. And bingo, it works like we wanted it to. Now you could save this as an alert from here, if this is something you wanted to use in your production environment. So there's one example. Let's come back to the showcase and look at, let's predict some fields, categorical fields. Let's try to predict hard drive failure. All right, that's kind of a busy search, but what that's doing is it's looking at the SMART, which is a metric that you get with your hard drives, self-monitoring, analysis, and reporting technology. I imagine there's some of you out there that know a lot more about that than I do. I just know what I just told you. But it's basically some metrics that you get out of your hard drives that are usable for this process. Let's just say that. We're going to use logistic regression. We're going to try to predict disk failure using these fields. Looks like SMART 1 through 5. We're going to split this into 70% training, 30% testing. And we're going to fit the model. And it already did. It already ran all that for us. We could have clicked this if we'd have changed something. And it looks like it gave us the precision, recall, accuracy, and F1 scores are all the same in this particular case. Looks like the accuracy and the F1 score is about 0.75, which is, it's okay, I guess. Let's try a different algorithm. I mentioned that the random forest classifier was often better than some of these others. Let's try that one. We'll click fit the model. Takes a little while. Looks like we got one that it failed recognizing. And we're waiting for the classification. 0.82. That's not too bad. Quite a bit better. Just for grins. Let's try one of these really sophisticated algorithms. Do the sport vector machine. Coming up. And the answer is 0.73. That was worse. It's worse than the simpler ones. So there you go. All right, let's do one more of these. Let's try a clustering kind of scenario. We'll try a security-related app like, or application like app usage. And it doesn't show it up here, so I'm going to show you real quick what's in the app usage CSV. This is a bunch of use numbers, if you will, across a spectrum of applications. So that's what that data looks like. And we're going to do standard scaler. It wants to, this is one of the algorithms, the spectral clustering algorithm, wants to use some pre-processing like the standard scaler. So we're going to apply that. And while I'm thinking about it, let me do this. Remember I mentioned the user guide. So we're doing clustering algorithms, and we're going to use the spectral clustering. You see how easy that is? We can go down here, we can read about what this is about. The K parameter specifies the number of clusters to divide the data into. So that's one of the parameters, one of the main parameters. There's some other parameters here, which doesn't really go into much detail on. So the other thing that you can do is you can hit scikit-learn.org and the user guide for that. Now, a lot of the stuff, almost all the stuff in that SciPy package, you will, that you loaded first, is based on scikit-learn sources. So what are we working with there? Spectral clustering. I don't know if that's going to work. Bring it. Oh, there it is. You click on this, and now you can get way down into the weeds with all this stuff. Way more than I thought I ever wanted to know about that stuff. But there it is if you want to really get into it. And this covers all the algorithms, this site. So try to make a practice of doing that. So anyway, we got the standard scaler. And it is going to work on Cloud Drive recruiting, remote access, and webmail. And then you'll see down here that it has created some new fields called SS_ Cloud Drive recruiting, remote access, and webmail. These fields contain the scaled numbers, and those are the data points that we want to use inside or use with this spectral clustering algorithm. So it has created this set of clusters here. Cluster 1 looks like a bunch of blue dots here. Cluster 0 looks like it's the green stuff. And then cluster 2 is some orange dots. And then I noticed that there's this outlier out here, which is like, wow, where'd that come from? Looks like even with scaling, you'll see how scaling, by the way, typically brings these numbers down to, very low values. But in this case, I can see that the SS recruiting number is 7.96. So that must be way off the charts, the original data value. So there's that. It did cluster this stuff together for whatever use that might have been to your application. But let's try another let's try Birch against the same fields. I meant to change that to 3. Let's do that again. I want 3 groups. 3 groups kind of made sense from what I saw from the data before. All right, so now we've got cluster number 2 is all the blue guys. Cluster 0 looks to be all the green stuff. And then cluster 1 looks to be this outlier here and one right up here in the middle of all these other things. Isn't that interesting? Not sure what I know about that, but in this case, you could use this to identify an outlier in this clustering model. So there's that. By the way, I mentioned it before, I'm going to say it again. In the user guide, let's see if I can find it. How are we doing on time? No, we're okay. In the user guide, there are the Smart Assistant, which is what we've been working with. It'll walk you through using any one of these that you want to work with. There's the experiments, which we're going to do an experiment next. Experiment's a little different way of doing this stuff. Very nicely laid out for you. And there's even some deep dives on like, well, we already looked at server response time, data ingest anomaly detection dashboard. How cool is that? I actually played with this myself. This is looking at your data sources. A couple of observations I made on it. You see how it uses count. There's a couple things wrong with this. This is really cool, and I suggest you try it. Got a couple of things though. Count, it's using counts to see if your data inputs into your Splunk environment are healthy. The problem with just count is it doesn't reflect the volume. And I have had situations with customers where an application group would turn on debug and the event counts didn't really change, but the volume increased significantly, as well as the license consumption and the potential cost. So you really want this to work with volume and not count. And you might want it to work across all of your data sources instead of just one. So there you go. There's some challenges to make that work better. So, all right, let's go back to one last exercise here. Let's do an experiment. Now, an experiment's where you work with the machine learning toolkit on your own data. Let's detect some numeric. Detect numeric outliers. That's category. Here we go. Detect numeric outliers. Well, let's call this detect CPU anomalies. Create. And basically, this is going to create a environment. Looks kind of familiar. But in this case, you're putting in your own stuff. It's kind of all on you. So I have a search here. This is going to, all right, what's wrong with this? Unknown search command time chart. Oh, there's a space in there. Should have been a duh. This is the CPU utilization for the Splunk server I have sitting here in my lab. It's running on Ubuntu. It's just 4 cores. And again, this is 10-second samples from the introspection metric index, and grouped into 5-minute sample periods, if you will, taking the 95th percentile of all of those. And I'm calling that the P95 CPU. And let's search for just the last 24 hours. We don't need all the time. So we're going to do some anomaly detection. We're going to use the P95 CPU field. We're going to use standard deviation. We'll call this 3. And I'm going to leave the sliding window, which is how many samples are used to create the average and standard deviation calculations. We'll leave that blank now. It can just work against the entire data set for now. And there we go. Not too bad. I'm going to open it and search. And go to visualization. Come down here to my chart, which of course isn't going to work right until I do table time. And this is P95 CPU, lower bound, upper bound. Did I get those right? Yes, I got them right. By the way, if you, I don't know if I showed you this before, but if you forget which order they go in and you do it that way, it doesn't work so well. So don't do that. So there you go. And again, you can save this in alert, or you can come back here. You remember we had this experiment that we were creating. You can save this experiment. Click save. And there it is. Now, you remember when we first went into experiments, we got all these boxes that kind of look like what you see in the showcase. Well, once you've created one or more, you'll come back up here and there's a group of these, depending on the type of experiment you're running, and you can see those. You can click this, and if this is something you were working on yesterday, and you want to come back and dink with it some more today, then there it is. It's left as you left it. The other thing you can do with that is, if you're pretty happy with that experiment, you can create an alert out of it. There's all the SPL and all the typical parameters in an alert that you're used to seeing, except now we have some machine learning conditions types of trigger. And you can send an email and do whatever, just like you did before. All right, so that concludes my presentation. I'm going to try to stop sharing and come back to there. We're done. Oh, not hearing you.
Yeah.
There we go.
Okay. Well, thank you, Jim. Thank you for the information you presented here on Machine Learning Toolkit. It's very interesting stuff. I hope you out there were able to glean some information and learn something new as well. If you had any questions, send them to support@kinneygroup.com, and we'll take a look at them and provide you a response back. Also, if you'd like to learn more about the performance and capacity analytics element or Atlas, or even expertise on demand, even our professional services offerings, send an email. We'll be happy to provide you some information and talk further. So with that, everybody have a great rest of your day, and we will see you again next month in January.
Okay. Ciao.